All right, today we're going to be wrapping up this section on language-based security by talking about enforcing language abstractions. Now, programming languages are actually a really fantastic abstraction. Computer science is all about abstractions, but programming languages, I think, are a particularly great one. They allow us to tell computers what to do in a relatively clean way. And as we all know from our own experience programming, when we think about instructing the computer to perform some computation, we're really using the abstraction the language provides to us to do that. You know, be it variables, objects, modules, functions, whatever it is, they allow us to really scale our reasoning and our thinking about computer systems. Problem is that language abstractions can be violated. They may not hold. Now, there's a few different reasons for that. One is simply that when we compile a high-level program down to a lower level of abstraction, it's a different abstraction that's going on. And so if you imagine compiling your favorite high-level language, OCaml or whatever, down into assembly code, then that assembly code gets linked against other components that were maybe written in different languages. Languages that don't have the same kinds of abstraction that OCaml does. And as a result, those interactions with other components might violate some of the abstractions that the programmers have been holding in their heads. There are other reasons why language abstractions might be violated. Even within a language itself, there are often very strange features of a language that we as programming language theorists often try and just politely ignore for the most part. Things like reflection, where you can have first-class values that represent some of the program structures or semantics. Unsafe code that deliberately violates aspects of the type system or abstractions. There might be dynamic code with perhaps eval being one of the most common examples of this, where essentially you take a string, eval that string, and it's going to treat that string as if it were a program and execute it in the current context. But even calling foreign functions from your program, so calling a function written in another language might end up violating your abstractions. There's a whole bunch of other reasons why the abstractions that we want to hold in our head as we write programs may fail to hold. Now, unfortunately, if those abstractions are violated, then our reasoning at the language level may not hold. And this includes reasoning about security. Right? All of the stuff that I've been talking about for the last couple of days has been talking about reasoning about security in a programming language model of the system. And if those language level ideas don't actually hold when we execute the system, what was the point of all the reasoning we were doing? The good news, though, is that there are a variety of techniques that are really focused on enforcing language abstractions. And what I'll say is that these techniques to enforce language abstractions both apply programming language ideas and techniques, but also by enforcing those language abstractions, they really enable sound reasoning at the language level and thus help lift the boat of language-based security and other techniques that we're using at the programming language level that we want to hold at runtime. Let's take a quick look at a few of these techniques. One good general principle is don't have executable data. So this might mean don't have an eval operator in your language if you're designing a language, or if you are trying to decide whether or not you want to accept code into your code base. Maybe you want to check to make sure it isn't using features such as eval. That said, though, it is often really useful to have limited forms of reflection where the program itself can manipulate the program or create new pieces of executable content. Analogous to, or within the same idea of executable data is with a database interface. Instead of using, let's say, a string-based interface that might be subject to an SQL injection attack, where the attacker provides what's meant to be an argument to a query, but in fact ends up violating the intended abstraction and providing a new and completely separate query. There are alternate approaches. For example, using prepared statements instead of arbitrary strings. Right? So this general idea of don't have executable data is often a really powerful one to help us reason about language abstractions. Another set of techniques that are used are about enforcing memory safety. A lot of the times, the way that language abstractions are violated is through violating memory safety, be it the type safety of memory locations or other aspects of the correct use of memory. So some of the techniques to enforce memory safety include things like fat pointers, where a pointer to memory includes not just the beginning of the region of memory that's meant to be addressed, but also additional information, such as the size of the available region. This can help prevent buffer overflows, which are a common way of violating language abstractions in languages like C, C++. There's a whole lot of work on software fault isolation, SFI, which is essentially rewriting the code at a low level in order to ensure that it approximately matches the intended execution of the program. So the key idea of software fault isolation is that it might be masking all memory accesses to make sure that the program only accesses appropriate pieces of memory, say within a limited region of the address space. Control flow integrity, which I at least group under SFI, might be ensuring that jumps are only to suitable targets. And this might be done by making sure that any basic block or function that you might be jumping to or invoking is appropriately aligned, maybe on a 32-byte boundary. Or maybe the system is rewritten to have a list of acceptable addresses to jump to. And any jump is kind of checked against that list. So what's interesting there is it isn't actually enforcing the semantics of the original language. It's just trying to reduce the possible number of behaviors to something that approximates it. So that is, control flow integrity isn't necessarily ensuring that the control flow of your execution matches the control flow intended in the original source program, since it might still allow a jump to a target that is a valid target to jump to, but just not at that point in the program. So these high-level ideas are really about trying to get something closer to the intended semantics. Yeah?
I don't think I completely grasp the definition of abstraction. Like you said, SQL injection violates the abstraction of SQL, and buffer overflow violates abstraction of C. What does abstract mean in this context?
The question of what is an abstraction. I think at a high level we're familiar with this idea of we get to ignore the details, right? We get to think about a complex system without needing to know all of the implementation details that underlie it. Now, what this means with respect to, let's say, the memory model in C is that we don't typically need to think about how memory is actually laid out on a physical machine when we are writing at a C program. Steve Zanzwick is the expert on this about the appropriate memory model, but a common one that programmers have in their head and is a completely reasonable one to have is kind of this Swiss cheese model of memory. That when you get a piece of memory, it's sort of this isolated region that you're able to access. And if you go beyond, if you access that region of memory beyond the appropriate bounds, it's undefined behavior. When you actually compile it down, run it physically on a machine, the memory is laid out in an actual address space. And these regions of memory might be contiguous with each other. Now, buffer overflow happens when you write beyond the boundary, and instead of halting, the program will typically continue, but having made a transition to a state that really wasn't permitted by the original language semantics. Now, with respect to an SQL injection attack, maybe it's a softer abstraction going on there. The abstraction there is that the programmer came up with a string that was, let's say, meant to represent a select query, where the user provided one of the arguments for the query. That was their intended abstraction. But because they were putting the argument into that query simply by string concatenation, it allowed a carefully chosen string, an SQL injection attack, to violate that intended abstraction. And instead of being an argument into an SQL select statement, ended up being two SQL statements, one of which dropped all of the tables in the database. Does that help with what an abstraction is and why those two examples are examples of violating the abstraction? Okay, thank you. Okay, yes, another question. There's a variety of techniques to try and make them efficient, but essentially they don't help performance. Software fault isolation approaches might do it in software. I remember Steve did some co-design, hardware and software, to try and make it more efficient. But in general, security never makes things faster. And trying to do things like enforce abstractions in a reliable way is probably not going to make your system run any faster. So the question is, how much cost are you paying in performance in order to get guarantees about, say, memory safety, enforced language abstractions, and so on? Okay, so those techniques, that pointer, software fault isolation, they're somewhat ad hoc, right? They're trying to restrict the possible behaviors at runtime, but they don't give direct guarantees that what happens at runtime necessarily matches the intended semantics of the source program. So let's think instead about compilation, compiling from a high-level language down to a low-level language, and think about how we might reason about language abstraction in that setting. Now, first of all, to give you an example to show that this is an issue, that when we compile from a high level to a low level, this is one of the ways language abstractions can be violated. Let's take a look at a Java-like program. This is from Patrignani and others. Who's familiar with Java? It used to be like the language that almost all intro classes were taught in. Okay, most people are familiar with it. Fantastic. So here we have a class account. It's got a private field. This modifier here, private, means that this field balance can only be accessed by code within the class account. So code elsewhere in the system shouldn't be able to directly read or write that field. Instead, they would need to access it through the code that that object, that class provides. For example, by depositing money into the bank account. Now, if this Java program were being compiled down into a C-like language, we might have something like the following, where an object, the data for an object is represented as a struct. In this case, it's got a balance field and a function pointer to the deposit method. And here is the implementation of this particular deposit method. Fantastic. The problem is that in this C-like language, we don't have any sort of private modifier here. There is nothing that is restricting other code from accessing this balance field. And so the abstraction that we had at the source language level, keep the balance field private, kind of disappears when we compile it down to the lower level. And if we compose it with other C code, that C code might legitimately access that field, suddenly make everyone a gazillionaire, and so on. So the goal of secure compilation is to develop compiler techniques that can preserve security properties of program components. So that is, so by program component, I mean components that will be composed with other components later on. Some of those other components might be malicious. They might have been crafted by an adversary. They might behave arbitrarily, and so on. So that is, the goal of secure compilation is to make sure that the reasoning about security that we do at the source language level continues to hold when we compile the program and actually execute it. And this is really about preserving those language abstractions, ensuring that the reasoning we're doing at the language level is in fact valid with respect to the program that we ultimately execute. So there's a variety of formal statements to define secure compilation. One common approach to it is known as full abstraction. So a compiler is fully abstract when it translates equivalent source language components to equivalent target language components. Okay. There's a lot going on there. It's a short English sentence, but there's a lot of complexity in this. So we are actually going to get to the point where we can see an explicit definition of full abstraction and understand it. But in order to get there, in order for us to define full abstraction, this idea of preserving equivalences from the source level into the target level, we're going to need to first define the notion of contexts and contextual equivalence. Out of curiosity, who's familiar with contexts? So that almost everyone, fantastic. So I have a definition up here. A context C is a program with a hole. The idea is that the hole can be filled with a program component. And once you've got a context, got a component, put the component into the hole, you have a whole program, a complete program, CP. So you can think of this context as being like a function that, given a component, will return a whole program, a program that can be executed. So we can use contexts to model external code that's interacting with a component. Let's see some examples of contexts. Here is a context in an ML-like language. Let f equal whole, there's the whole, in f applied to 0. Okay, so we can have a component, in this case, a simple function from x to x plus 7. When we put that component into the whole, we get the whole program. Let f equal fun x goes to x plus 7 and f applied to 0. Awesome. This is maybe the setting where you're most familiar with seeing contexts in a functional setting, but the same idea applies in other languages as well. So here, for example, is a context for Java. So we have a class main sitting inside a package main with a main function. The whole here, I don't actually have an explicit dot inside brackets, but in Java you could think about this as I'm going to take this context and take a component in the form of a file, compile them, put them all together, and that will give us the whole program. So if we take as a program component that snippet of code we saw earlier about an account, the idea would be that these two things together, these two classes together, give us a whole program that we could in fact execute, starting from main, creating a new account, and so on. Yeah?
This suggests that linking programs together, that linking context is somewhat similar to a program context on the previous slide. Is that true, or is that?
Yes, that's a good way to think about it. That linking is one of the ways that you end up combining components. And so if you end up thinking about linking and we're just waiting for one more component to be given to us, and we link that in with everything else to get an executable, that's kind of that's I think a very reasonable equivalent of a context at a very low level. Right. Cool, thank you. Okay, so we have this idea of contexts, right? Essentially functions from program components to whole programs. You can now think about the idea of contextual equivalence. So we're going to write that P produces O if P, a whole program, produces an observation O. I'm not going to dig into what the observations are. Maybe it's one of the observations might be that the program diverges, or maybe that it terminates with a particular output, and so on. So we're just going to be a little hand wave about what the set of observations possible are. But with this idea in mind, we can define contextual equivalence as follows. So two components, P1 and P2, are contextually equivalent if for all context C and all observations O, C with P1 in the context produces O if and only if that same context C with program component P2 produces O. So let's try and develop some intuition for this. Note that contextual equivalence quantifies over all possible contexts. So what it's saying is two components are contextually equivalent if essentially you are trying to tell them apart and you're trying to come up with a context that will be able to distinguish whether you're given P1 or P2. And you can't do that. No matter which context you come up with, you put in one of the components and it produces an observation, or that observation could have been produced by either P1 or P2. So with respect to all of the contexts you have available to you, you cannot distinguish P1 from P2. Yes, question?
Is it at the source level or the target level?
We're going to be using the same the same idea at different levels. So you can think about this at the source level, if that's convenient. We're also going to be using the same idea of context and contextual equivalence at the target level. So this is kind of language, and at a high enough level, this concept is language independent, right? And we will be using it at both the source and the target. Okay, so two components are contextually equivalent if there is no context that can tell them apart. That is, they behave exactly the same for any possible context. Any questions about this definition? Yes?
I don't see it like in the previous example you gave where we had a private field and then that abstraction disappeared. Can this capture that? Because like if this is the source level, the context knows about the private field and cannot access it. And if
Right.
it's the target level on both sides.
Let me just hold that thought for about 2 or 3 minutes, 2 or 3 slides, because at the moment, we're getting to the idea of full abstraction that is really going to be talking about compilation. But at the moment, to get there, we need this concept of contextual equivalence. So at the moment, just think about this at, let's say, the source language level. And in fact, here's an example. Okay, here are 2 OCaml-like programs, right? Both of them are computing factorial. So the one on the left, yeah, I'll let you take a read of the implementations. And now my question for you is, are they contextually equivalent? So that is, could you come up with a context that is going to have one of these 2 functions plopped into the whole, and you get to use that function essentially just by applying it to values, and then, or whatever else you can do in your contexts, could you distinguish these 2 components? Could you figure out whether you were given the component on the left or the component on the right? So I'll give you a few seconds to think about it. Are these hands up questions or knowing the answer?
Kind of a question.
Okay, go for it.
In this case, the one on the left has cases for 0 and everything else. The one on the right has a case where n is less than or equal to 0. Does that imply that on the left, if n was less than 0, it would just go on forever?
Ooh, that sounds like a really subtle thing going on here. But these are integers. So yes, the intent is that these are, in fact, not contextually equivalent. That there is a context, there is a program that you can use that distinguishes them. And your insight that, yeah, if I pass in a negative integer to this program will diverge or end up with, maybe a stack overflow or something, whereas the one on the right will terminate immediately for this first case. So these components are not contextually equivalent. We have at least one context that can tell them apart. What about these 2 components? Sum to n. Okay, one of them is using a reference to accumulate them. The other one is doing it recursively on the right. So hands up if you think they are contextually equivalent. Hands up if you think they are not contextually equivalent. That is, there is some context that can distinguish them. Okay, I gotta say, I'm not an OCaml expert. But my understanding is that at least with standard OCaml context, not using any of the deep dark magic that can, for example, measure the, maybe measure the amount of memory usage and things, that you wouldn't be able to distinguish the behavior of these two components. That is at least in terms of their input-output behavior, providing the argument to them and getting the result back, that they behave the same. For people who did think they were not contextually equivalent, that is, there was a context that distinguished them, did you have a particular context in mind?
Yeah, the right one is not very recursive, so it will crash numbers.
Crash for big numbers? Okay. Yep. I'll come up with another example sometime that is intended to be contextually equivalent. Or really, I will note that that point actually brings up the idea of whether components are contextually equivalent depends on the expressiveness of your contexts, of the things that you can do and the things that you can observe in the whole program. And so, you know, I'm kind of appealing to OCaml here, which is dangerous because OCaml is a real and complicated language and system. And I guess I should be very careful to define semantics so that we can more easily pin down whether or not things are equivalent. But what I really wanted to do is get to the key intuition behind this, that components are contextually equivalent if within the expressive power we have in that language, we have no way of distinguishing them. And intuitively, we should, in many, many languages, we do actually have programs or components that are contextually equivalent. That when you plug them into a program, the program is going to behave exactly the same way, regardless of which component you put in. Now, that might be different implementations of the same module interface, for example, if those implementations are done well. Sorry, there was another question, I think. So, okay. Again, doing a hand-wavy appeal to a real language to build intuition, here's something that's kind of similar to our bank account example. Here we have two Java program snippets. They have a private field, secret, which is an integer. And they have different implementations of the set secret field, one of which sets secret to 0, the other sets secret to 1, but they both return the same result. Now, assuming that, I probably should have provided some more code here. Assuming that there is no other code within the class, that is, there is no other code that within Java, at least normal Java semantics, ignoring things like reflection, that are able to access secret, and there is no other code whose behavior depends on the value of secret, then these two components would perhaps be contextually equivalent, right? Even though they're differing on the value of the secret field, no context, nothing that's interacting with this code, is able to distinguish them, is able to really access that secret field or distinguish any behavior that differs from them. Yeah. Okay. Okay. So often when we're talking about contextual equivalence, we'll sometimes restrict these set of observations to either being convergence or divergence. Sorry, there's a typo there. Terminating, converging are synonyms. And the intuition for that is it can simplify our theory. There's only two possible observations, termination or divergence, without really limiting our expressiveness. And this is because if we are trying to figure out if have a context that is meant to distinguish components by testing whether the value returned was equal to 42, well, then you could write a context that tests whether the value is 42, and if it is, diverges, and if it doesn't, terminates, right? So that is, we can convert kind of any other observation into either convergence or divergence. As I was saying, though, our ability to distinguish components is really based on what our contexts are able to do. And typically, at least in the functional programming setting of contexts, we're not able to observe, let's say, how long a computation took, right? So this idea of contexts is actually, and what they can distinguish is very tightly coupled with some of the ideas that we've been talking about earlier about what can be observed by an adversary. Okay, within this case, the context limiting that observational ability. Okay. I'm not going to be getting into proofs about contextual equivalence, but I will say that reasoning about contexts can be very hard. And in particular, with contextual equivalence requiring this universal quantification over all possible contexts, it can get, some of the proofs can get a bit gnarly. It is possible to use other equivalences, by similarity, some trace-based equivalences, which can be easier to manipulate or reason about in proofs and can be shown, and if they are as exactly as precise as contextual equivalence, which can be shown sort of once and for all, you can show that we're still working with the same concept, but in a slightly easier way. Okay, do we feel comfortable with the notion of contextual equivalence? Okay, so we're going to build on this to get to full abstraction. So a compiler is fully abstract if it preserves and reflects contextual equivalence. So that is for all components P1 and P2, the source components are contextually equivalent if and only if the compiled components are contextually equivalent. So here what I'm using is these double brackets here to indicate the compilation of P1, compilation of P2. Okay, there's still a lot going on here. It's, you know, one line of mathematics, but there's a lot to wrap your head around. So what does this mean, this full abstraction? Well, let's think about just one direction at the moment. So if we think about reflection as the backward direction, so that is if the compiled components are contextually equivalent, then the source components are contextually equivalent. This follows from compiler correctness, right? That is, if the compiler is correctly compiling the source program behavior to the target program behavior, then we're going to get this reflection, this backward direction of the equivalence. So for example, imagine that we had a compiler that compiled every single source program to return 42. Okay, it's not a very useful compiler. It's not a correct compiler. Every single program always just returns 42. And note that it doesn't satisfy reflection, right? P1 and P2 could be different source programs that both get compiled to return 42, so they are contextually equivalent. However, the source components are not contextually equivalent, right? So the idea here is that one direction is following from compiler correctness. The fourth direction is preservation. That is, if source components are contextually equivalent, then the compiled components are contextually equivalent. Now, what this is really ensuring is that the target language does not have any additional ability to distinguish components. Right? What this is saying is that if at the source level it's impossible for us to distinguish P1 and P2, then when we compile those components, it continues to be impossible to distinguish them. What this means is that when we compile down to the lower level, and we think about contexts in our target language, we still do not have any additional ability to distinguish those components, to break the language abstractions that we had at the source level. So that's kind of the intuition for this preservation, and also hinting at why it might be useful as we think about security. right? That essentially the compiler is correct and it's preserving these source level language abstractions. Target contexts don't get any additional ability to distinguish components. Yeah, question.
How are you defining compiler?
You know, I haven't had enough coffee to be able to rattle it off the top of my head. It's essentially along the lines of if I, at the source language level, if I have a whole program, all of the observations that I have at the source language are available at the target language. Anyone want to help me out? Is it an if and only if the set of observations at the source level are equal to the observations at the target? Or is there a subset relation one way or the other?
It depends on whether you have non-determinism and allow refinement.
Yeah.
Usually the target is a subset that can be used.
Okay. Thanks, Steve. So essentially, the observations that you have in the compiled program are permitted by one of the permitted observations at the source language. But note that compiler correctness is a property of a single component, essentially. We're saying the compiler is correct on this component if the behaviors of the source component are a superset of the behaviors of the compiled component. Contextual equivalence, full abstraction rather, is actually talking about pairs of components and executions at both the source and the target. So it's a more complex property in many ways with full abstraction than with compiler correctness.
So 42 was one of the possible behaviors of the source level. And then you always compile it to return it. Wouldn't that satisfy like your data?
Well, if your compiler was compiling every single program to return 42, there will be programs where returning 42 wasn't an observable behavior. Say a program that computed the factorial of 5. Okay. Let's think about trying to achieve full abstraction. So that is, we're trying to both think about techniques we could use to show that a compiler is fully abstract. One thing I'll point out, first of all, is that the compilers we use on a day-to-day basis are not fully abstract, right? If we, when we compile down from a source language to assembly language, what you can do at the assembly language level is far more finer-grained and powerful than you typically can at the source language level, right? You have assembly language contexts typically have access to the entire state of the process and are going to be able to observe a lot more things than at the source language level. I'm going to talk briefly about static and dynamic techniques for achieving full abstraction, but both of these techniques may require what's known as back translation. Back translation is the idea of proving that given any target language context, there exists a source language context that does the same thing, right? So you can imagine that if you were able to have this back translation to show that for any target language context, they could, let's say, distinguish P1 and the compilation of P1 and P2, there exists a source language context that could distinguish the source level versions of P1 and P2, right? If you were able to construct a back translation or prove that one exists, then that's kind of taking you well on the way towards reasoning about preservation, about the backwards direction. There are some techniques for reasoning about full abstraction statically. That is coming up with a target language that has a type system that is sufficiently restrictive to rule out any sort of target level context that doesn't have a corresponding source level context for it. And then the proof might be about type preserving compilation, showing that a well-typed source program gets compiled down to a well-typed target program, and that any well-typed target language context has a back translation to a source language context. So that's one approach. Doing it statically, doing it before you've ever run the compiler or run the program. Some of the techniques, though, for enforcing full abstraction are actually, if you will, doing so dynamically and modifying or choosing a very particular target language so that the operations there are restricted in various ways, right? So it may not be necessarily restricting runtime behavior through typing the target language programs, but more by just designing the runtime system appropriately. So the sort of things that might be used are cryptography. It's using cryptography in the target language, say to seal up various things, maybe even perform homomorphic, using homomorphic encryption to encrypt only in to compute only in very limited ways on particular values might be one of the ways that we can make sure that the context at the target level are restricted in what they can do with the components we care about. We might be able to insert runtime checks so that, let's say we are talking, our components we're talking about are modules. We somehow insert runtime checks at all of the ways the module could be interacted with to make sure that inputs and outputs are appropriate for the semantics of the source language. So essentially using runtime checks or a runtime monitor to make sure that any interaction with the target language context corresponds to a context that we could have had at the source level. We might be able to use things like security architectures to help ensure this. Address-based layout randomization might help us prevent low-level memory address attacks from being applicable, or at least with reasonable probability. We might be able to use trusted execution environments like SGX or Trust Zone in order to protect the components appropriately and make sure that all interaction with them corresponds to interaction that's okay with respect to the source language semantics. Any questions at the moment about full abstraction? I will say, I'm giving you 15 minutes of full abstraction and could easily do an entire course on these ideas. Yeah?
So the compiler with full abstraction gives us the security guarantee with the source language. But do we lose anything if we do that?
Do we lose anything if we had full abstraction? I will say full abstraction is hard to obtain. It's hard to actually write a fully abstract compiler, particularly against realistic target languages that we care about. So your question was, what do we lose or what do we gain? What do we lose? Ease a whole bunch of the infrastructure that's currently in place to compile and run programs. Efficiency. Yeah, it requires a lot of effort to be achieving this, and yeah, I'll leave it at that. Yeah.
In a security context, do we care about the reflection direction, only about preservation?
In the security context, depends what your notion of security is, but often we care about correctness, the idea that a program is doing a correct thing.
If you have non-determinism at the level of the source, but you make it more deterministic at the level of the target, you might be correct for some notion, but you might not achieve reflection.
Let me think that through. I'd need to think about that more to see.
If contextual equivalence is as we have the same set of observation, but in one case you optimize one of the two programs by removing one observation.
Yeah. I need to sit down and check this, but I believe if you had a compiler that was refining behavior, so that is the source language allowed a larger set of observable behaviors, and your compiler chooses some of those to implement it, I don't think that's incompatible with full abstraction. I believe that you could still have a fully abstract compiler. I need to think about that more, actually. It's a good question about how non-determinism fits in. With respect to verified compilers, a lot of the time the restrictions are made about determinism in order to more easily reason about correctness and prove it. So I'd need to think more about how that interacts with the definition of full abstraction. And again, if people in the audience have insights, go for it.
Is it fair to say that if we compile, say, OCaml into C, then almost by definition we won't have full abstraction?
Yes, in general, yeah. Let's imagine going into C and you are losing some of the information hiding that you have with modules.
It's not clear how you would mitigate this by, are some of these dynamic techniques? Is there some practical way that you could then do something dynamically?
Yeah, so some of the approaches, there are compilers that are proven to be fully abstract, and some of the techniques they might use is compiling a component into something that can be isolated. So that is strongly isolated from other parts of the system, and that interactions with that component can be mediated. And runtime checks to make sure that this message being sent to the component, does it actually correspond to a meaningful source language message? If it doesn't, let's say the message gets dropped, or some standard well-known response is delivered. So this is essentially making sure that the component is only receiving, is only interacting in a way that corresponds to a valid source language context. But what it requires there is isolation, being able to isolate the component and make sure that the available interface for it is not as rich as what you'd see in a standard snippet of C code or assembly code or so on. Okay, so full abstraction preserves and reflects contextual equivalence, but that may not be the only property we're interested in preserving. There might be safety and liveness properties that we care about in our system. People familiar with safety and liveness, the idea of like trace-based properties? Many people? You can think about properties as being predicates on the execution trace of a system. Hyperproperties are predicates on sets of execution traces, and it turns out that non-interference is a hyperproperty and not a property. Don't need to go into the details of this, but the key idea is that full abstraction turns out to be not strong enough to enforce these. And indeed, it's maybe incomparable with some of the things we care about, and achieving full abstraction might, as I've talked about, can be really challenging. And if we don't actually care about preserving contextual equivalence, but maybe just care about preserving, let's say, a safety property, maybe we can get away with less effort while still achieving what we care about. So to give you an example of why full abstraction isn't enough, suppose that we have a compiler that takes programs of the following form. So I'm using blue here for a source level program. Here's a function that takes a Boolean x. There's some expression e that uses the argument x, and it compiles it to this target language program, which I'm writing in red. We're going to represent Booleans as natural numbers, 0 representing false, 1 representing true. Takes a natural number as an argument. If that natural number is a valid Boolean, that is at 0 or 1, then it does whatever the compilation of the function body is. Otherwise, if the value was 2, goes into an infinite loop, pulls f of x again. And for any other natural number argument, it returns 42. So that is, it checks if the input is a valid representation of a Boolean, and if so, it behaves correctly, the compilation of E, but otherwise it does something insecure. Maybe it terminates, it returns 42. Turns out that this is fully abstract for reasonable notions of context at the source and the target language level, both of them being functional programming languages. But it doesn't preserve a safety property of, let's say, never up at 42. So that is the idea being that if a source program preserves a safety, if the source program satisfies a safety property, we'd maybe like our compiler to ensure that the compilation of that program also satisfies the safety property. And so clearly this doesn't satisfy the safety property never up at 42. This source program here never outputs 42, but the target program does if we give it an appropriate input. Yeah?
Can we not have a target context that checks if the output is 42 and now you have
Yes, we could have a target language context that checks if the output is 42, but note that it won't be able to distinguish two source language components that are contextually equivalent. So if I have two source language components that are contextually equivalent, I won't have a target language context that can distinguish them, even with this translation. Okay. So we could come up with some other notions for a secure compiler. One of them is called robust trace preservation. The idea is that a compiler satisfies RTP, robust trace preservation, if compilation preserves every trace-based property. So by that I mean for any possible property, pi, as I said, is a set of execution traces. For all programs P, if P satisfies the safety property, that's what this line here is saying, then the compilation of P satisfies the trace property. Okay, so if we had a, so this might be a useful property. A useful aspect of a secure compiler, that it's guaranteed to preserve any sort of property, including safety properties, never do this bad behavior, and so on. We can actually express it in an equivalent way that doesn't require quantifying over every single possible property by instead using traces. So this is an equivalent property-free characterization that we might want our compiler to satisfy, that for all programs P, for all target contexts, and for all traces, if the compilation of the component can exhibit some trace T, then there exists some source level context that exhibits the same behavior T. Yeah?
So do we not need a way to relate like event traces or target traces to source traces and vice versa? Do they may look different?
Source traces and target traces might look different. So we're kind of glossing over that at the moment. If you did instantiate this for a particular source and target, yes, you'd need to be a little more careful about what are my events at the source language, what are my events at the target language, how do I map between them, and so on. But for simplicity, these definitions are assuming the same set of traces. We might be concerned not about every trace property, but maybe only safety properties. So you could come up with something similar that quantifies this time over all safety properties. I won't go into the details of what that is. But the idea is if the source for programs P, if P satisfies the safety property, then the compilation of P satisfies it. And there's also an equivalent property-free characterization, which is actually kind of interesting for those who are familiar with the topology of properties. You can think about this M here as being a finite trace prefix that witnesses the non-membership in a safety property. I talked briefly about hyperproperties, and we could think about a compiler that satisfies robust hyperproperty preservation. That is preserving every trace-based hyperproperty. And again, the definition is relatively similar for all possible hyperproperties. That is sets of traces. Any behavior we see at the source level, if the set of behaviors at the source level are in the hyperproperty, then the set of behaviors at the target level are in the hyperproperty, with equivalent property-free characterizations that I won't go into. Now, these ideas of robust hyperproperty preservation, robust trace preservation, and so on are from a paper by Abate and al. From about 5 years ago. They actually present a whole lot of different definitions that might be reasonable for secure compilation, showing you the colors are a bit washed out, but the diagram is a bit more interesting in the paper. Full abstraction is in here. It's actually hidden right there, robust trace equivalence preservation. So essentially preserving all trace equivalence properties from the source to the target turns out to be equivalent to full abstraction. So this idea of secure compilation, I think, is incredibly powerful, incredibly promising, and really bridges what is a significant gap between the story that I've been telling so far about using programming language ideas to model systems, reason about those models, but then bringing it back to reality. If the thing we really care about is not executing that source program, but instead executing the compilation of it, that's kind of a big area for us to be concerned about. There's a whole lot more reading that you could do about this, including Amal in previous OPLSS's, instead of talking about logical relations, has talked about secure compilation. So those are a great series of lectures if you want to dig more into it. I've got about 20 minutes left, and I'd kind of like to change gears for a bit. Go off on a bit of a tangent. Don't worry, it is relevant. I want to talk to you about weird machines. Out of curiosity, who's heard of weird machines? A couple of people. Excellent. So a lot of this is new. All right. Before I talk about weird machines, let me talk about buffer overflows. So let's consider the following C code. This has a classic vulnerability where it's got a buffer allocated on the stack, and then it copies input into that buffer. So the challenge is that an adversary might call this vulnerable function. So here you can think about the stack going downwards. Here's the stack frame for this vulnerable function. And an adversary could call this with input that has x86 exploit code written into it. So what will happen is when we call string copy, we'll copy the input into the buffer. It's going to fill the buffer and actually overwrite other important parts of the stack, including, let's say, the return address. So that when this function returns, instead of jumping to the original caller of this function, it will jump to this address, the address of buffer right here, which can contain arbitrary exploit code. So that's bad. We can prevent it. This idea of don't have executable data. One common technique is to make sure that the stack is not actually executable, right? So that when we jump to the address of buffer, the machine will blow up and not start executing the code. But even so, this might still be vulnerable to an attack, one that makes use of existing code. So libc, the C standard library, is around on most systems, and the address of libc is guessable. So it might be possible for the adversary to set up the stack so that we overwrite the return address here with the address of some of the system function in libc. And moreover, we overwrite the argument build area, the area that when that system function in libc starts executing, it's going to go to read what the argument is, with, let's say, the address of the string /bin/sh. Okay, so we overwrote the return address with the address of the system function, and overwrote this with the address of the string. Maybe that string already existed in the system. Maybe it's an address in the payload of the attack. So what that will mean is we could jump to system and open up a shell on the machine. Not good. It actually gets worse than this. Even if we could figure out how to prevent that return to libc attack, we might be vulnerable to what's known as return-oriented programming. So the idea of return-oriented programming builds on the concept of a gadget. A gadget is simply a short sequence of machine instructions that ends with a return instruction. And you can imagine an attacker looking at a binary and actually automatically identifying gadgets, snippets of instructions that end with a return. And then the key idea of return-oriented programming is to chain these gadgets together. So that is to take the address of these gadgets, to overwrite the stack so that there's essentially a sequence of return addresses so that we will jump to one of the gadgets, execute that short sequence of code, do a return, and thus go to the address of the next gadget on the stack, and so on. And so the idea is that these gadgets might be performing operations that the adversary cares about, but they might also be setting up the machine state for the next gadget to do something useful. So one gadget might load a specific value into a register, and then the next gadget is going to read from that register, and so on. Now, it turns out that you can identify these gadgets automatically, and smart people have come up with compilers, where you can write some arbitrary code, and it will compile it down to a set of gadgets, and essentially come up with an exploit string that you could use that chains these gadgets together to perform the computation you want. OK, so here's a security problem. One of the things we can do, though, is think about how we might use formal methods to formalize, think about these kinds of attacks. Once we can sort of understand what these attacks are, we might have the ability to rule out not just return to libc attacks, not just return-oriented programming attacks, but entire classes of attacks that we can generalize, that we can think about through formalization. Now, there's been some recent work on weird machines that presents a really great perspective on this, about a formalization. So what I'm going to do is spend a few minutes telling you about the weird machine formalization. It's based on the idea of that the programmer had something in mind that they were intending to implement. And we can capture that as a finite state machine. In fact, a transducer that takes input and produces output. But let's not quibble about the details. Let's just assume that we have some state machine that that captures the intended functionality of the system. To be a little more concrete about this, an example I'm going to give by Dolian, who presented this work on weird machines, might be a secure server that is complex enough to be interesting, but simple enough that I can present right here and define the security guarantee. So the idea is that we're going to have a machine that remembers password secret pairs to be retrieved later. And when you retrieve a password secret pair, it removes that pair from the machine, from memory. And just to keep things finite, we'll assume that we can have at most 5,000 password secret pairs. Security property that we're going to get to is that intuitively, you need to know the right password or guess it with whatever probability you have of guessing that password in order to learn the secret associated with that password. OK, so we can actually sit down and explicitly design the finite state machine. The states are essentially the sets of password secret pairs, ranging from the empty set to all single pairs, P1, S1, up to all possible sets of 5,000 different password secret pairs. And then we can describe the intended state transition for this. This is representing it diagrammatically, but basically you could set up the transition function appropriately to be, take in an input of a password secret pair and essentially, update memory, or if the password is specially marked to 0, to try and retrieve that secret from memory if you have it already, so on. We can set up a security condition for this by setting up a game, like a game for a cryptographic protocol, where you can kind of say something like, an attacker is going to choose some transducer to interact with this system. The defender chooses a password and secret according to the uniform distribution. The attacker connects their finite state transducer to interact with the machine and runs it for a certain number of steps, and then sends a guess of the password and secret. And then what's the probability of them actually being correct? Has to be essentially sufficiently small based on how many steps they were allowed to take. So very much a cryptographic style game. Now, when a programmer is actually doing an implementation, they will be writing some program that is intended to implement or emulate that intended finite state machine. So let's suppose that we have some particular machine, Cook and Reckau RAM machine. It's a Harvard architecture, not because I'm from Harvard, but because the Harvard architecture is one where code and data are separate. The code cannot be treated as data. They are stored in separate memory. Let's see, we have some 32-bit memory. We'll treat the first 6 memory cells as registers. We have some instructions that we can use to manipulate those things. The details aren't so important. Just the idea that this is a machine that we could use to implement the intended finite state machine. Now, there are, as you might imagine, many different ways that you could implement the intended finite state machine. Let's consider 2 variants. One where we're using a simple flat array for storing pairs of values. Okay, so we just kind of, no sophisticated data structures. We essentially just search through memory to find matches when we're looking for matches. To add another secret password pair, password secret pair, simply find the first empty one and throw it in. A second variant, we might imagine, could be more complex. 2 singly linked lists, one to keep track of free space in our memory, and the other one to be the linked list of the password secret pairs. You manipulate those singly linked lists appropriately as you add secrets and check for them. Okay. So in this setting, we have the intended finite state machine. We have an implementation of it. And now we can actually talk about what are bugs in the setting. We can actually explicitly define bugs because we have this intentional specification in the form of the intended finite state machine. So let's call the implementation machine CPU, and let QCPU be the set of states of the implementation machine. And essentially, a bug has occurred if there's an implementation state that doesn't have a corresponding state in our intended finite state machine. There's kind of a little more detail you might need to go into. We need some abstraction function to take us from states of our implementation to states of our abstraction, of our intended state machine. The sane states are the ones for which alpha is defined. There really is a direct mapping from the implementation state into the intended finite state machine. But the implementation might take multiple steps to implement what was a single step transition in the intended state machine. So if this was the intended state machine making one transition, we have Q1 and Q5 that correspond to those states. In the implementation machine, it might take several steps in order to perform that transition. So we might have some additional states in our implementation machine that are sort of transitory, used to implement valid transitions. So then we can get to the point of defining weird states. So these are states of our implementation machine that are neither sane nor transitory. Now, there might be a number of sources of weird states. It might be errors when writing the program and allowing, let's say, a buffer overflow. So that when we have a buffer overflow, we have suddenly transitioned to a state in our implementation that doesn't correspond to any of the intended states of our original program. But maybe we also have just bit flips during execution. You know, these things do happen occasionally. There are actually attacks. The row hammer attack is a famous one that can increase the probability of bit flips occurring in a system. Okay, so why is this called weird machines? Well, the idea is that in a classic view of a machine, there is a program with instructions, and that program is accepting data, input, and as a result, transitioning through states. you can end up summarizing the sort of transition states into saying, we have an input, some number of instructions, and get to a corresponding state. Now, the normal way of thinking about it is, as I said, that the instructions down here are the program, and the program consumes the input as data. But you can actually flip this view of things and think about the program as being data from the attacker's perspective, and what the attacker is providing to the machine as being the program. So that is this is like the return-oriented programming, right? Where the attacker was producing a program in the form of data, or in the form of a sequence of gadgets to jump to. So in essence, the data that the attacker is providing to the system is kind of like programming some kind of weird machine, causing it to do these unintended state transitions that might be doing things such as operating on memory, revealing secrets that they shouldn't be doing, and so on. So that is, in an implementation, we might have this implicit weird machine that an attacker can program by providing input that causes that weird machine to do strange things. And so the way to exploit one of these weird machines might be to do some setup, to do some interaction that does correspond to normal interaction with the machine, to get into a state where something, buffer overflow, a random bit flip or something, moves us into a weird state, whereupon the data provided by the attacker is essentially programming this weird machine, causing it to do strange things. With respect to modeling the attacks that an attacker might have, this idea of some initial states that they want to get into from whence they launch their attack. So the setup stage, getting to the right initial state, entering the state of the weird machine through some exploit, and then programming the weird machine. At a modeling level, we might think about power of different attackers, maybe one that can, at an arbitrary program point, stop execution and choose any bit in your implementation machine to flip. Or maybe they're more restricted. They can only flip certain bits, maybe non-register bits. Maybe they can only stop the program at certain points in the execution to change limited bits. And that might, and so these are suitable abstractions from buffer overflow attacks or row hammer attacks to kind of talk about a very general and powerful model of an attacker. It turns out that of those two implementation variants I talked about, variant one, the one that just uses a simple flat array of password secret pairs, is not exploitable. And essentially, you can prove that by showing that any bit flip the attacker could make, you're still going to be staying within the sane states, within the intended states. Right? By contrast, that second variant that had singly linked lists manipulating free space in the list of password secret pairs is actually exploitable. And I don't have time to go over an example exploit, but essentially you can set it up, set up some known password, the attacker sets up some known password secret pairs, the defender inserts their randomly chosen password and secret, then the attacker flips a bit to mess up the pointers and essentially make sure that one of their known values now looks like the password to get the secret that the defender put in. Yeah, question?
Here the attacker can only blindly corrupt things but not see the secrets, is that right?
Right, they can corrupt the machine by flipping a bit, and then by, quote, programming the weird machine, then be able to, let's say, violate security by learning a secret. Yeah. And so that's the idea with, they might overflow a buffer, and then as a result of that buffer overflow, get the machine to do unintended things. Okay, so this provides a perspective on weird machines. It's kind of cool, right? It generalizes a whole lot of vulnerabilities into a relatively simple model. But does it give us any insight into how to actually prevent these vulnerabilities and build secure systems? So what I want to do is turn to another piece of work from about the same time came after this work, which was really casting weird machines as insecure compilation. The idea being that an exploit is behavior in the target program that doesn't correspond to behavior in the source program. So we can find these things explicitly. In the interest of time, I'm going to really just jump to a couple of key things. The nice thing about this work is it generalizes Dalian's approach of weird machines, but it does so using the vocabulary of language-based security. And in fact, what it's able to do is show that robust hyperproperty preservation exactly characterizes compilation for which there is no weird machine exploit. Right? That a compiler that satisfies RHP does not have any exploits in the sense of Dalian's weird machine exploits. Okay, so why did I do this? I've got like 3 minutes. I'm happy to chat afterwards in the break. So why did I do this? What is the moral of the story? And it is not, as ChatGPT is suggesting, either kindness or heredity. So I think weird machines was actually a really fantastic approach of application of formal methods to this problem. It kind of cleanly characterized a whole range of possible vulnerabilities. But the subsequent work that connected it with insecure compilation, robust hyperproperty preservation, was able to connect it with existing security definitions, and moreover, connect it with ongoing work and how to actually build these compilers in a general way that can achieve this freedom from exploits. So let me take a step back from the moral of this lecture and talking about secure compilation and weird machines and the benefit of language-based security, and talk about the moral of this the series of 4 lectures. If we look at this diagram that I've been showing you repeatedly over the time, to be honest with you, the moral is really what I said in the first lecture. These formal methods are a fantastic approach to reasoning about security, and programming language techniques and ideas are a wonderful fit for that. It allows us to come up with useful models for systems in the form of programming language calculi. These have effective reasoning techniques that we can use to reason about security and other aspects. Because we use programming languages to implement real systems, a lot of the time the reasoning that we're doing in these models actually translate to effective, efficient, practical mechanisms in the systems we're building. And moreover, if we can figure out this preservation of language abstraction, it lifts all the boats. It enables the reasoning at this modeling level to actually apply more firmly in execution systems. So with that, I really want to thank you for your time. Go forth and research these ideas, or in the words of ChatGPT, go forth and research. Thank you very much. I really appreciate your attention over these 4 lectures.